Hi, all. Today I continue the forum. We're going to talk about weight of gravity. So today will be the last classical one, and then the next one will be the quantum. So I start from last time, and I wrote this. This metric, special metric on the space like manifold. This comes from the foundation of the four-dimensional one, where this now this E are the triads, and you can see actually these are actually the can come from the pullback of the tetrads or turbine quantum, and we'll see where they come from the action, the Valentini action.
So these indices go from 1 to 3.
Yes.
Okay.
Yeah, by Latin indices run from 1 to 3, and these are the space indices, and I are the speed indices, so the flat ones. Okay, this one, as we have already seen that it is invariant under SO3 transformation, the defined transformation on the triads that were fixed A can be thought of as vectors in R3, and so there is an isomorphism between the defined representation of the SO3 on R3 and the adjoint representation of SO2 on its only algebra. So it is therefore it is needed to see that we can write this as a phrase of J, where this I are the generator of SU2. So they are just the Pauli matrices multiplied by I, and actually we also write as minus I alpha. So it means that if we simply have the trace here, and this trace here actually comes from the metric on SU2, then if we apply the adjoint representation on tau, where you are just SU2 SU2 element of the SU2 group, then we see that by the property of the trace, also this U1 cancel with U. So we have exactly the same metric which is invariant under the adjoint transformation.
So first of all, I don't see the factors. If I have Pauli matrices, I take the product. If they are the same, I get the 1, which is going to be the minus the 2 i's. It's going to be a minus a quarter times the unit matrix. And then I take trace, I get minus a half. But we have 1 there, so the to be exactly the same.
Yeah, up to 4. Minus 2, yeah.
Okay.
Yeah. So yeah, thank you for this minus 2. So we see that eight is the last, in just, oops, okay. That's the reason how our J. So it is under the adjoint, unjoined, representation of the field. Okay,
It's not a joint representation, it's a joint action.
yeah, joint action on it's on the algebra.
Right, but it's not, because if you say a joint representation, you might think that the dimensions are.
No, of course, no, of course. Yeah. Okay, so now we can define this object here, where we have this E determinant of a J. This object here, so we see there is a density of weight 1, because this one inside with the determinant of square root of sorry, with just the square root of LQG. Okay. Minus QB. So it is of weight 1, and okay, so this is of course this metric here can also be expressed in terms of this densified triads, but now it is not important.
Why minus?
Why?
Why minus?
Oh, yes. Yeah, it is spatial one. So yeah, okay, we can express this in terms of the density triads, but for now it is not necessary. What is important here to define the free space, that is, we want to connect now the ADM formalism to this triads formalism. Okay, so we started from the ADM variables to a B and DAB, where P is the momentum with respect to Q, and we are moving to some object here and EAI, because this E will not be the coordinate, but will be the momentum with respect to something else, because it is of weight 1, likewise P. So we want to define the coordinate on the phase space in such a way that we have this structure. So how that we find that object? We say that this K is the exterior curvature and it is symmetric. Now we define this K to be KAI I. So we just don't pay attention to the contraction because it will be just with the delta counter. So I can just write it as. Yeah, we define like this with this object K. And now one can see that we can express, remember this P in terms of the exterior curvature. Okay, so from the Poisson bracket between P and Q, it comes from that K is exactly the one that we're looking for. So it's a long calculation, so I want to avoid that because it's nothing conceptual.
I didn't understand the logic. I mean, you didn't define the KA.
Mhm.
I mean, I thought I knew what the KAB is, but you sort of try to define it in terms of.
Yes, this is a connection, this K. And this comes from the action, the Palatini action. We will see that. Where it is just the time component of the connection. That is, if we have R here, okay, this is the Eisenhubert, okay, but we also can start with the Palatini because we know that in absence of other fields, the Palatini is the same Einstein with the equation as that comes from the Eisenhubert action. Okay, so it's not a problem that. Now this R can be written not only in terms of the metric, but also in tetradic formalism. And in tetradic formalism, okay, that will be just okay. So
This is carbon, right?
this is
a carbon, you just divide by carbon and you divide by 1/carbon.
A, yeah.
Oh, it's a carbon.
Yeah.
Isn't it usually 2?
Actually, yeah, it is 8 pi g over
Yeah,
e
and
to
it
four.
was 16.
It will be 16, but some actually, yes.
So this is 2s.
That will be with 2, sure. One can take actually the what's called not modified in metric units, the reduce, I think. But yes, I mean, you're right. Actually, if you define k as to be 2 pi g over c to the fourth, this will be with 2. Okay, but actually, okay, I can have it here, but doesn't mind the way here because it's just a constant. So I can actually write it as it is. And here we can write actually depends on omega, which is the connection in first order formalism. And this will be the spin curvature. This spin curvature is written in terms of the spin connection, which are treated as independent variables. So the way it will be to write all of these with omega mu and then with mu. Okay. Yeah, I think the line is incorrect.
Yeah.
Okay, so now what we want to do,
With the minus last two.
yes. Okay. It would be plus there. Okay, so here what we want to do is to split this space-time into the one that we know, so R cross sigma. So we create this foliation, And once we have that, we can write this difference, okay, in terms of those new coordinates on r and sigma. Then, after that, we, after all the calculation that we can do, it we want to vary the action with respect to the spin curvature. Okay, get the action field equations. Okay, and then it turns out, as you know, that the spin connection has to be the Levi-Civita one. So everything comes, it will be equal to the Einstein-Hilbert. And then in the track formalism, you find the field equations.
I would probably formulate it a bit differently because, you cannot to really say that the spin connection will be the Civita connection because they don't even have the same index structure or symmetries or anything like that. Of course, you can express one.
I mean, the Levi-Civita spin connection. I mean, not the Levi-Civita lens.
What is the Levi-Civita spin connection?
That will be, this spin connection will be, I mean, that's a sum of the Levi-Civita one plus something else. And that something else is the consortium.
Okay, sure. That's good.
That's not with the conversion to be zero, so we're left with the metric Levi-Civita one.
No.
Yes.
So what you call unitary spin connection, that's the one which have 6 terms of the e's, like
6 terms
of the e's. Yeah. So basically E, D, E, 6 times.
E, D, E.
No, he's saying EDE is 0.
E, no, this is partial derivatives.
Yeah, he's saying that part is 0. It's just saying that you take the Civita connection.
No, I think is the co-torsion is like 0.
Yes. Wait, if the
That's
conversion is zero,
the G bracket.
That's not one. Yeah.
if the conversion is zero, then the torsion is zero.
Right. Okay. So what's your what's the formula for the Levi-Civita spin connection?
Well, in the spin connection actually is quite a mess. If I remember well, I want to write it as this is the Levi-Civita, so with the parties to say. If I remember well, this has to be a new I in new comma mu j.
That's the formula I was thinking of.
Yeah. Okay. So okay, this has to be actually right for it. No, J, then we have, remember it is plus or minus here with K rho and K sigma, and that's it.
Yeah, that's the 6 terms.
Okay, so that's what you have put in the torsion position.
Yes,
Right?
yes.
But,
So it's purely metric and
but I wouldn't call it Levi-Civita because Levi-Civita usually you get from imposing compatibility with the metric. And the spin connection is compatible with the metric.
yes.
Coming from the
Yeah, but the Levi-Civita has to be torsionals. I mean, both of them are G compatible, but what the Levi-Civita is torsionals. So as I said, if the contortion is zero, then the torsion is zero, and so this omega has to be the Levi-Civita. It's called the Levi-Civita spin connection. It is called. All right, so that's the setup here.
So will you now explain how they?
Yes,
External curvature is a component of it.
Yeah, I'll get to that. Give me a second. Just keeping you on track.
So.
Don't erase. There's no like.
Yeah, but then I don't have space here.
Yes, you have to get there.
We have two big black holes.
No, but that one I want to leave it like that, you know, I don't want to raise.
But
I also have here, but then I cannot move to one. I mean, once, I mean, this one is not important, no. So if you
Erase.
this one, just to answer to your question, sheet one. So this one, what we want to do is to say, split that M to the different prism R sigma, where now this we have this coordinate T for R and all these XA for sigma. Then we pull back on the space like only so that we can reduce the metric here into the Q1, so the space only. Then after that, we can write all the terms here, and well, it is quite a mess. I don't have that forward too, but maybe. Uh, okay, so we pull back so that we can write this G, which is equal to the determinant E4, to note that it's to be not a triad, but with the turbine. This will become the loss function and Q, which is the determinant of Q. Then this E mu I E mu I sorry, I want to write this omega mu I j, first term. This is to be E mu 0 E mu. Since this is antisymmetry, that's something that I forgot to say. Antisymmetry in the IJ indices that come from the annihilation of the covariant derivative on the Minkowski metric. Okay, and for the triads with the Kronecker delta. So this is antisymmetric in IJ. So it means that the component 0, 0 is 0. So we have this. Okay. Mu I. mu, and then this space like the indices move to this EX. So when we count T0, E, I dot plus okay, so here we have that okay, only say this becomes with minus. Yeah. Okay, and lost. Okay, this is just the first term, so that's why I don't want to run everything there. So this is quite long, but the point now is the following. So we have these components of the connection.
But it's differentiate.
Yeah, differentiate. So, and now this now becomes triads, and this ET0 and ETI, and also EA0 will be just, I mean, this one will be just the first term of the 4x4 matrix, this row, and then same. So we have exactly the derivative of the connection. And we don't have the derivative with respect to the triads. You see from there. Okay. So what we want to do after all the computation there is to define the momentum. Okay, so with the momentum, what we have to do is to vary the action with respect to the derivative of the connection. Okay. And if we follow this, then what it turns out is that once we write these triads in terms of the density triads, because here we have the determinant. Okay, what it turns out is that the triad is a density triad will be the momentum with respect to a specific component of the connection. That is
Yeah, but now you raise the question of the understand.
yeah, no, I'll write it. So now, yeah, we have that EAI will be the variation as with respect to omega A 0 I dot. Okay. And now, let's forget about the constraints, we get the
Actually,
up to K.
yeah, actually, that is a point with respect to functional differentiation that when we talk about functional differentiation, it doesn't really make sense to talk about, say, with respect to omega dot. What we really want to do is to say partial derivative of the Lagrange density with respect to
Partial derivative of the Lagrange term with respect to
Lagrange density.
density.
Yeah, okay, depending on what you mean. I mean, I mean the integrants. The
Yeah,
integrand of
yeah, so understand. With respect to this,
yeah.
no, this is a functional derivative.
You want a functional
Yeah.
derivative? But
You can always define the.
yeah, but okay, but do we agree that the other thing works?
Cannot say no.
The point is basically that when you are in the action, then the variables with dot and on dot are not really independent. So that
And not.
so therefore, it strictly speaking, does not make sense.
Okay, is there an advantage of using the action instead of Lagrangian? Like in mechanics, we usually define the motion with where we differentiate the Lagrangian with respect to the velocity, and not the action. So is there why do you want to use the action instead of the Lagrangian?
So because
Do you agree that if you use the Lagrange density, then you get the angle you want?
you also have the integral with respect to the time in the action there.
Sure.
Okay, so. Yeah, that would be the integral, yeah. True. But I believe there's also. This works.
No.
Well, if you have the Hamilton Jacobi.
There is no omega without the dot in the action, so it doesn't really matter. What you make, it's the same. Because there is no curve in the action which does not have omega without dot. I mean, you don't care about the other derivatives. You just take the space.
In the action, I can just partially integrate
Yeah.
with all over the velocities.
That's true.
So there's no.
It doesn't make sense.
If you just take the Lagrangian, just integrate over space.
So if you take the Lagrangian, as more to the Lagrange density, then you can get away with time, but then you can define
Yeah.
velocity.
Okay.
Yeah. That's pretty.
Thanks.
Um,
Okay, so now.
so you use script for Lagrange?
Mhm.
So you use script for Lagrange density?
No, this is all the Lagrangian.
Yeah, so you have integrated over space.
Yeah, because in that, once I reduce that d for x into the d3 x, I define this with that d3x. So just apart from the derivative, but for the integral, yes. Yeah, so it turns out that this up to factor k to be 1 over k here, well. But I mean, we can also use the geometrized k, so we can put kappa to 0 as 1, so it doesn't matter now. Yeah, okay, so this is, okay, and then we also have the momentum with respect to the laps and with respect to the shift, okay? And also the momentum with respect to the other components of the, uh, can I say the connection, because it is independent, okay? Now, this piece here, omega A 0 I call it K A I.
Well, I mean, omega is a connection, K is a curvature.
No, it's K
Well,
A
this is what
B
it says.
is the curve, yes, K A B is the curvature.
Right, so connection it cannot be a curvature. They transform different connections, one tensor, curvature is a tensor.
But this is the, and,
That's
mm,
omega without the dot.
yes, without the dot, without the dot. Well, let me tell you,
I mean,
this is how it is defined.
It might be because he now, because of the 3+1 splitting, has less.
sure, but I mean, there is a definition of external curvature.
Right.
Just put it in form of a metric and calculate, and then one should somehow see that this has the right properties in that sense.
Uh, and that will be just, mm, K A B. Honestly, I cannot answer your question.
Yeah, no, but so, you know, I'm just reacting to what I see. So, you know, if somebody says this is the expression of curvature, for me, I like to connect it to something that I know, which is some other formula for this curvature. And this formula that you wrote down, I don't recognize, especially when you rewrite K as omega. I mean, this relation is trivial.
Yeah.
What you're saying, omega spin connection is the external curvature. That's what sounds new to me, and if it's correct, then it's interesting because you know I can learn something from it. So that's why I'm asking.
Well, this is we said this by definition. Okay, we will also say that.
So I'm fine with the definition.
Yeah.
I'm calling this thing K.
Mhm.
Okay, but then you said it's the external curvature. So that's
So is
K A B connect.
is KAB a tensor?
K A B.
A flat
This
tensor.
this is the external group.
So is it a
Again,
tensor?
the tensor.
But on the right hand side you have some.
Yeah, that's what they was asking.
Yeah, so there's a problem.
Right.
Yeah.
So, what is the alternative definition? I remember something like, I've seen it for a hypersurface where there's a normal vector and then it's something like a covariant derivative.
right.
That's what you're thinking of.
So somehow maybe one can show it here using this split that you did. That can be written as well. I don't see it at the moment, but maybe there is something in the appendix of the Word on this.
Well,
White can red, I don't know, but here is. Very interesting. That's very nice. Okay. This color is the color one. Now this is equal to the plus one. Okay. This is the final this. Sure. And but it doesn't say KAI for us to be. Okay. This is from the ATM. And then we connect it to this here.
Right, so here this is the definition, right? So here you have covariant, like Clark said, covariant is normal.
Yeah, that's the definition of the.
And then they are somehow using. Okay, some formula calculated to show that you can actually. Okay, it's fine. So this is the calculation that I'm asking.
Okay. Yeah, but.
That is the hard. Okay, but so for me, yeah, without this, I feel. Okay.
Yeah, I know, but if you, I've never seen it. Okay, so. This is the way it works. So what you see from here is that from the action, this is E is the momentum with respect to this omega that we just talked as K. And if you write this K in this way, then from the ADM, for some bracket from the ADM, it turns out that exactly E is the momentum with respect to this K. So in the at the end of the day, now so now here you have from the ADM. Pass through the yeah, that's right. This is to be A, I, and E, E, A, I. Okay, so now these two are conjugate variables. And so you see that the commutator between this, which is just a space line, so it is with fixed t, and sorry, let's try with e first. Zero, and you have delta AD. Okay. So we have this symplectic structure. But this is not all, because yes, we can now define the covariant derivative compatible with the triads. Okay, but first, I want to tell you that we can exploit exactly the, because then I mean this is yes a definition, but also it's a long way, but it counts also the following of this one, no? Okay, now I can define this GAP instead as the J.
So how are these defined?
Yeah, just
Is
yeah,
it the
okay.
inverse?
Hmm?
Is big E the inverse of big E?
Yes, yes.
It's not densitized in some.
Yeah, that is the style. Yeah.
It is densitized, it can be densitized in different ways.
Yeah.
So it's densitized so that the scale
As we said, it is the okay. And the sorry, the BI is 1/E E okay. Yeah, what you've done here is just to divide by one over the determinant, so some other, and here we take this as instead the unsymmetrization. Since this is the symmetrized is the only part that is non-zero because of the definition of the extrinsic curvature, it means that the unsymmetrized part in this method part is zero. Okay. So this one has to be zero. But also we can say, okay, now we can change the indices by constructing with triads. Okay. So that this G, we can write this GIJ as sorry, okay. This is zero, and this is called the rotational constraint. If we have parallel, we why it's called the rotational constraint. That is on three. Okay, anyway. So now this is, as we said, it is antisymmetric. So is it possible to relate this to some other antisymmetric matrices that we know, 2 by 3, is with the generator of SO3. Okay, so this will be a combination of those generators. Therefore, we can write yes, way to G in terms of the generators of SO3, which are also generator of SO2. So, yes, this is called the rotational constraint and also comes from the action. So now I want to make this comparison. Now, if we follow the alternate picture, so that since we know that the generally is a constrained system, we have constraints. But in the ADM, we have seen that we have two types of constraints. One is called the vector or differential constraint, and the other is the scalar or Hamiltonian constraint. So we have four, because the differential has three, so we have in total four constraints. Here in tetradic formalism, actually, we have one more type of constraint, which is the Gauss constraint. Because it said the Gauss constraint said that the action is invariant under SO3. Okay. So yeah, you see that it's invariant under for the action by SO1 3. Okay. So if we reduce and put on sigma, we are left with SO3. And therefore, we have also this type of constraint that is written as this. Okay, where now this gamma is the Levi-Civita spin connection. Okay. How did we get to this? Why there is this epsilon, I ask? Because we have the gamma ij is the three-dimensional spin connection constructed only from the trials, not from the field line. This is, as we said, this is for fixed A. This is a antisymmetric 3x3 matrix. So we can write it in terms of the generator of S3, which we know can be written as 1K and some other part as a combination. So gamma A K.
So is G the same G as?
No, it is this plus something else. Yeah, because the Gauss constant is called G, so maybe I call them the same. And that is the rotation. This is the Gauss constraint, so it's better to write like this. Right? Okay, from
Oh, okay. That makes sense.
from the action, it comes that if we set the constraint, this is one of the constraints. Okay, so this has to be 0.
Why do you call it Gauss?
Yeah, because this can be written as the covariant derivative of E. Yeah. Has to be equal to 0. Now I'll show you why this is the covariant derivative with
Well, that I can see.
but this is the limited right, so maybe you can say you can say that the covariant derivative, I just wanted to write it here in the days, say API has to be doesn't matter up or down, right?
Is it primary or secondary?
What do you mean by this?
Does it come from some commutator with other constraints? Or do you get it directly from?
The definition of this covariant. Yeah, no, this is the definition that the S will be compatible with the trials. Okay, so we have this derivative, which is, partial derivative and also acts on the space index, so we have this very cheap stuff.
I would expect it to be secondary, because it's secondary.
It's
in
always
the-
secondary.
But second,
But that's, that's like,
you mean secondary constraint. Oh, sure, of course, because the value is just the location of the momentum. If they're equal to zero, then are primary constraints.
so this is.
All the constraints that come from, the Gauss, the Economics and the Hamiltonian are all secondary constraints. And there is no tertiary constraint. And all of these are first class, so they generate KG. Actually, this is not always true. This is an argument because Deere claimed that every first class constant generate gauge, but actually Teitelbaum and some others show that you can have first class constraint, but they are not gauge solution. But those are mathematical construction. Every physical system, it is true that for every physical system that you start with far, the first class constraint generate first class constraints generate gauge. Yes.
Yeah, that's called the theoretical conjecture.
Yeah, that's a conjecture, so no one proved that, but
Why do you want to minus in the last?
yes, because I reached this issue.
No, in the.
Here?
Yeah.
Why I have to have the minus? Because this one, I can write it as epsilon I K J.
Depends on what your conventions
J omega A K.
are. That doesn't really show you, I mean, if your convention is that the connection, it's like the first index that you connect, then you can flip the indices and make the plus.
Yeah, this is with the
No,
plot.
that doesn't really change it.
No, it should, then we have nine I J K.
That did not answer the question.
You mean why we have
No.
minus here?
In the second term,
Yeah,
you're just writing.
you always have the plus in the covariant.
No,
with
I
I.
always have the minus.
No, well, it depends on how you define it.
Exactly.
Yeah, you define this. Yeah, I mean, it depends on the convention that you choose. But which of them? All right, and then actually you have to say that this omega inside weight. This
Well, I
double,
mean,
that's a different.
okay, yeah. So, yeah, I don't like it. So anyway, yeah, you're using again that you can raise and lower indices trivially. I would write the I downstairs. To be really.
No, it doesn't matter because this is,
That's what I said.
this is going to raise minus.
It doesn't matter,
plus.
but it's like unconceptual. So.
Because maybe you use a different signal too.
No.
Yeah, if you have the plus minus minus minus, then you have to be careful with this, which.
Yeah, so the point is, when you have to be careful sometimes, why not have a convention where you don't have to be careful?
Okay, so. Yeah, so this one, as I said, can be written as the covariant derivative there. Because if you define this covariant derivative compatible with the trials and therefore with the density trials, we have this dA, dA. Yeah, I can write this gamma, we'll see. Plus, sorry, so it becomes minus with gamma A K E A J. But then, since this is a density, we have a further term, which depends on the weight. And that is minus the weight, and in this case it's 1. Yes, sir.
So why didn't you write it in the previous line?
Because this one, oh, you're right. Yeah. Minus A C A E yeah, I C C B. Yes. Probably, okay, that's the same.
Well, this should be,
No, that's
okay, yeah, because we want to trace that,
Yeah.
yeah, I know.
So now you see that this cancel, and therefore you get to this. So it's perfect because now we have exactly the Gauss, and this has to be 0. Okay, it's a bit too long, but okay, this is the Gauss. Then no.
You have so much space, I mean,
Because I want to write the constraints. I can write just one constant here, another constant there.
so you should have written that stuff over there.
That's right. That's right. And this is the Gauss. And this generates SU2. Then we have another one. First order. Okay. This exactly. From the effort comes also this one, which is the rotation constant. Okay. Then we have the diffusion of Eisenman, which can be written as right. To okay, if of course, so as to be in here, K actually it is not a connection that I mean, when we have these two partial derivatives, then the connection that comes from the only the special ones are a priori not symmetric because we are in the first order. Okay, so it means that now we cannot write it as covariant derivatives so far. Otherwise, we should have also gamma A and also gamma AB. Yeah. Then we have the Hamiltonian. D or so D square root. Yeah, square root of yes. Yes,
Like the
that's
fourth square root of,
hmm?
like the fourth square root of Q.
Because this E is uh, yeah, from here. Yeah, so then it has to be third E. So E four. So when we have square root, we have E squared, which is Q.
So this is Q squared.
Q squared. Yes. So then
One Q.
one Q. Okay, that's quite nice. Uh, should be, yeah. Yeah, yes, and this five. Now, this generates diffeomorphism. This generates actually uh, it is more complicated because you have the normal vector to sigma in the space like hypersurfaces, and this H gives you actually the flowing along the time of that connects two hypersurfaces by a time-like curve. So it gives you actually the flow on what, I mean, the evolution of those hypersurfaces of the population. But actually, it is, I mean, that's just an idea, but it is not strictly as that. Okay. So once we have this, so there are many other things to say. So there is also one in the first order. Actually, I haven't seen this one. There's no name. Uh, we have P, U, J. I want to all this. This is and this. As I did that from a but it comes from the first order formalism. So when we evaluate this to be equal to zero, from this we see that the connection has to be Levichin. We ask why. First of all, here it doesn't matter actually if it is Levichin or not, because if always old. Because that vanished, I mean, that cancel out as we have seen. But here from this one, the only possibility to make it 0 is that this omega T0J has to be exactly in the formula that we have written for the LQG spin connection. Has to be exactly that one. So the 0J component, T0J component of that. So if you enter this with that, all of this cancel. Otherwise, no.
We're explaining it has to be.
Has to be torsion free. And then, okay, so this is there for the Jupiter. And now another thing is that, I mean, also LQG, so it means that here we can subtract it as a covariant derivative of K. But the most important thing is that can we combine these two, the Gauss and the rotational constraint? Yes, because in this part here, we have this piece. So here we have the pure latitude, and here we have this K. So we can combine both two and say this is a differently. Here this is going to be weekly 0. So this holds only on shell. So we can rename this one to another connection, but there is also an additional thing that we have to say. And the additional thing it comes from exactly from the symplectic instruction, from this. Why? Because this one, this Poisson bracket is invariant under our scaling by some complex number. If we have what over gamma, this is the last part of course. You know that we call it R. Yeah, that's the same as one sort. Now gamma, which is theoretically a complex number, lives invariant this Poisson bracket. So what we can say is that we can use instead of the original ones this new rescale ones.
But isn't everything inside real? I mean, everything inside is that real? I mean, your E's and your K's, I mean, they are real quantities, right?
Yeah.
Real
Yes.
quantities.
Yeah.
So it's
Once
a
they-
little bit.
Yeah, you have to go to complex general
Yeah,
activity here.
right, so why
That's
not, why not go all the way Octonian to?
That's what we don't want. But I'm saying that arbitrarily, there has to be, can be a complex number. And initially, Ashtekar, actually not only Ashtekar, but also Stern and others use this gamma to simplify the Hamiltonian constraint because it is not polynomial in E. That's another matter, but that can simplify that piece. If you choose gamma to be the imaginary unit, either I or minus I. But then it is more complicated to go to complex general relativity. You have to do some real conditions and so on. But then this gamma, called the Mirzi, Barber-Mirzi, can be thought of just as a real number, and we can quantize if this gamma is an arbitrary real number by the thema streak, so on. So yeah, then this gamma can be thought of just as a real number. And so what we can do here is to say, okay, let's use our new variables. And say I call this with gamma.
But by the way, in the direct delta function, is there some kind of is this also densitized?
Yeah, it has to be inside, of course.
So there is a square root of g and having on that inside there.
Yes. Yeah, of course, it does have, because this has to be the density also that one. Yes. So be with the square root of minus g. Square root of q. Yeah, so this one we can write it as this. Well, we call this just gamma 1 over gamma 1 and we gamma. So this one becomes this gamma ak with gamma, which means in terms of the new rescale the factorials plus and this gamma b. What it turns out is that when we express this in terms of just triads, it turns out that this is invariant under a scaling transformation. Sorry, scaling of the triads and therefore the scaling of the matrix. You can see in that Tima's book. So if you want, I can show you why. Otherwise, you can take it as it is. Gamma AK is invariant under data scale. But it is quite also easy to see that because in both in this gamma has a Q with indices up and the derivative of the Q of indices down, right? As a definition of the Levchivita. Therefore, since this gamma is a constant, doesn't matter the partial derivative, and therefore the gamma cancel. The gamma up and gamma down. Because this here, it is instead as we said, E, I, gamma, gamma. And this actually exponents 1 square root of E. Okay, I don't remember, I think it's just 1 over gamma E. I thought this is the same. So because of this,
The opposite.
yes.
But what observe this,
Hmm?
this guy has to be the opposite, not that. Which is, oh, it's bigger one time.
Yeah, as gamma K plus, we can write it simply as gamma mu. Now this new convection here is called the Ashtekar-Barbero connection. Also called Barbero because now that gamma we take it to be real. So this is our new connection, definition of a new metric compatible covariant torsionless covariant derivative.
So you say it's torsionless still, the new connection? Or not?
Hmm?
Is the new connection?
Yes, it's a new connection because instead of just gamma, we also have
Sure, is it torsionless?
yes, it is.
Is it compatible with the rest?
Yes,
So
it's
how-
compatible with trials, of course, as before.
right, but you know, so now you're saying there are two different connections,
Yes.
both torsionless
Yes,
and compatible with the rest.
on shell.
I don't know what that means. But,
Yeah, that has to be.
Not compatible or partial, so I'm sure you both equations.
Yes. The point is that, as I said, this constraint gives you the fact that the connections will have cheap. But on shell, you also have this rotational constraint. Okay,
But I would still need that offshore this connection to be the same.
on shell.
Yeah.
Yeah, I mean, this is on shell.
The originator and the Ashtekar Barbero.
Yeah.
Plus, very important, only one unique. Social was metric
Well, it's okay, that's um now the point is that in the compatibility and the fact that it's Levi-Chev torsionless, we have just this gamma. Okay. But since we are in the here triadic formalism, we have also a gauge transformation acting on the triads and leaves the Lagrangian invariant. Okay. So the fact that you have this on shell rotational constraint, it means that you can rotate by S of 3 the triads and the action will be invariant. So it is also how to say that, but if you're left on shell, you have to find only this piece here. And can actually zoom more. Yeah, I'd say that just when you want to be on the on the submanifolds that you get from gauge fixing. Why gauge fixing? I didn't tell you why, but I mean, what is the gauge fixing? But in the action, we have fear binds, which are general. They have no, say, they have 16 components, so they are 4x4. But the metric in generality has 10 degrees of freedom. So it means that we have to use now the Lorentz group. We can use it to gauge fix. What we gauge fix is the boost. Okay, so we are left only with the SO3, and that reflects exactly that invariance. So you still have this rotation of triads, which gives you the action environment. So I'd say that only if you fix and reduce this the Lorentz, that you can get this new connection. That's the way I'd say. Okay, I know that I'm doing, yeah, it's 3:30. So I have to stop, otherwise it will take 1 more hour. Also, but we have to study the Poisson bracket between software to see that they are first class and what is the real meaning of them. For example, you have this or this Gauss constant, and we want to see explicitly that they generate SU2 transformation, gauge transformation. And that the action is invariant under that. And the meaning of this one in terms of, I mean, rewriting this in terms of the field strength with the connection, try to show that this Ashtekar Barbero is as well, likewise K is conjugate to E. So they find the same symplectic structure. So there's still quite something else to say. So that's why I'm going down. So do you have any question?
Maybe about the scaling of the units parameter. What are you scaling? The space-time coordinates?
No, not the coordinates, just the trials.
Oh, the trial themselves.
Yeah.
So the K gets used because it's.
By scaling this E, it means that you are also scaling the metric.
But you explain the non-densitized E.
Yeah, but also the same with the densitized only.
Yeah, no, I mean like, because it's not clear to me how you get the scaling into the bracket, because it seems like, you sort of did it arbitrarily such that it is invariant. But now it makes sense. If you scale the small e, then the densitized E and K get this contribution with IFS.
Yeah, it's
Okay.
it's not the uh, Yeah, since this is the definition of E. That's right, means that if we rescale, okay, 1/gamma. It means that now this EAI, you can check it, is rescaled at the square root of gamma EAI. And so the metric QAB becomes, sorry, not this one over square root of gamma. And this becomes 1/gamma QAB. So what you're doing is to rescale the metric. It's not a conformal transformation because it's just a, so it's just a rescaling. If you want to conformally transform the metric, it means that you need an additional field, scalar field, and as to have also its associated momentum, so it's like adding matter. If you want to keep the competitive structure, essentially competitive structure, so the canonical transformation, but that's a matter. So with the scaling factor, I would say, but you have to scale also the disconnection at the same time, otherwise you will.
Independent.
It depends.
You scale the K independently or it?
No, that has to be simultaneous. I mean, if you rescale Q, you have to rescale K. It also comes from this,
But that is exactly what we call file scaling.
yeah, just scaling,
File scaling.
Yeah, I mean, there's a special,
not conformal.
yeah, there's a special
Okay.
code for that, you know?
Yeah.
If you just change the metric vector function,
Yeah.
you call it while, and
Yeah.
if you change the coordinates such that the metric changes by a factor, that's conformal.
Yeah. Okay, and last thing, say, you can see that it's, you have fundamental formula. So when you rescale this by having 1/gamma E and D, it is the same, right?
Yeah.
So it's, what's that? Yeah, so we, I also had something else. So I have to go. Oh, yeah, yeah, okay. You also have now, since you have this imbalance under the scaling, the generator of the scaling.
But what is why do we put in this image parameter other than, I mean, so it seems like we are just packaging the constraints. And that would make sense if it is indeed complex, because then we will get two independent conditions. But if it's now real, then it seems like we are missing one condition.
No,
Because if you only say that the some linear complete have to be zero, and it's real.
no, that's why if it is C, you want to then impose some real conditions.
If I say in the case where it's not C, where it's
Yeah.
real,
Yeah,
then it seems like when you just make this linear combination, then instead of having two sets of, I mean, what you call rotation constraint and Gauss constraint, then you have added them together. And it seems like now you're only imposing
the real one.
yeah, we are still in the real case, but then you're only imposing some linear combination.
I outside the complex case. because it's quite complicated.
Yeah, I'm not talking about the complex case, I'm talking about the.
Yeah, because in that maybe you're right, you can cause that, the difference with the real one, just not a real one.
I don't think that answers my question.
Yeah, that will make more sense. Because it will package nicely.
Yeah.
Based on the constraints.
Yeah.
If you allow this.
Exactly.
You have another question? Thank you.